You think you know what fast looks like. You think you understand what cold means. But on July 1st, 2025, a telescope in Chile spotted something that rewrites both. A visitor moving at 130,000 miles per hour, not slowing down, not orbiting, just passing through like our entire solar system is nothing more than a highway rest stop. This is 3I Atlas, the third confirmed traveler from another star system, and everything about it is wrong. The carbon dioxide plume stretches 350,000 kilometers. The trajectory cuts backward through the ecliptic at 175 degrees, retrograde motion that defies expectations. The chemical signature screams impossibility. 8 parts carbon dioxide to 1 part water when every comet we have ever studied runs the opposite ratio. The James Webb Space Telescope stares at this thing and finds isotopes that match Earth. The orbit aligns perfectly with our planetary plane, arriving at the exact moment to pass Mars, Venus, and Jupiter within months. The statistical probability sits at 0.0005%. If you value documented astronomical discoveries and factual space science like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. This script is researched and factual, using sources from NASA's Goddard Space Flight Center published in August 2025, and the James Webb Space Telescope NIR spec campaign data published in Astrophysical Journal Letters. Not generic observatory reports, but direct instrument analysis from humanity's most advanced space telescope. Now back to the information. The Atlas telescope system in Rio Hurtado, Chile catches the first glimpse July 1st, 2025. Object designation, A11PL3ZD. Movement pattern suggests hyperbolic trajectory. Within hours, 3 more observatories confirm what should be impossible. The Zwicky Transient Facility finds pre-discovery images dating back to June 14th. The object has been cruising through our solar system undetected for weeks, 410 million miles from the Sun when discovered. Already inside Jupiter's orbit, already committed to a path that will take it behind our star and out into the void forever. The Minor Planet Center processes the orbital calculations and assigns the designation. 3I Atlas, third Interstellar, the letter I carved into astronomical history 3 times now since 2017, but this one moves differently than its predecessors. 1I Oumuamua tumbled end over end, cigar-shaped and silent. 2I Borisov behaved like a normal comet with a normal water ice signature. 3I Atlas splits the difference and breaks every rule in the process. The eccentricity hits 6.141, the highest ever measured for an interstellar object. The trajectory appears almost perfectly straight because the hyperbolic curve stretches so extreme. At 6.2 times the eccentricity of Oumuamua and nearly twice that of Borisov, 3I Atlas moves through space like it owns it. The retrograde inclination tells the real story. 175 degrees tilted from the ecliptic plane, moving backward against planetary rotation while staying precisely aligned with the disk that contains every world we have ever known. This alignment occurs in 0.2% of possible trajectories. The arrival timing for close encounters with 3 major planets occurs in 0.0005% of possible scenarios. Dr. Avi Loeb and his team at Harvard calculate the odds. A natural object ejected from another star system should approach from any random angle, should arrive at any random time, should follow any random path. 3I Atlas arrives on schedule, on course, on a trajectory that maximizes planetary encounters while minimizing detection time from Earth. The coincidence stretches beyond statistical comfort. July 21st, 2025, the Hubble Space Telescope locks onto the target, 277 million miles from Earth. The image resolves a teardrop-shaped coma stretching behind the nucleus. Dust particles ejected by sublimation create the signature tail. The nucleus diameter measures between 440 meters and 5.6 kilometers. The uncertainty spans an order of magnitude because the dust cloud obscures direct measurement. The infrared signature puzzles astronomers immediately. Most comets show water ice sublimation as the primary activity driver. 3I Atlas shows carbon dioxide as the dominant emission. The spectroscopic data from ground-based telescopes confirms cyanide gas and atomic nickel vapor. Normal comet chemistry in abnormal ratios. August 6th, 2025. The James Webb Space Telescope points its near-infrared spectrograph at the interstellar visitor. The observation window lasts several hours at a heliocentric distance of 3.32 astronomical units. The spectral analysis covers wavelengths from 0.6 to 5.3 micrometers. Every molecule in the coma leaves its fingerprint in the infrared spectrum. The results shatter expectations. Carbon dioxide dominates the emission at 129 kilograms per second. Water vapor manages only 6.6 kilograms per second. The CO2 to H2O ratio hits 8 to 1. The highest mixing ratio ever recorded in a comet by 6 standard deviations above the trend line. Carbon monoxide adds 14 kilograms per second. Carbonyl sulfide contributes less than half a kilogram per second. Water ice particles smaller than 1 micrometer float in the coma, sublimating thousands of kilometers from the nucleus. The isotope ratios tell a deeper story. Carbon-12 and carbon-13 appear in proportions similar to Earth. The material formed in an environment with familiar stellar nucleosynthesis, not alien chemistry, just alien location. The carbon isotopes point to formation beyond the CO2 frost line in a protoplanetary disk, around a star with metallicity at least 40% of our Sun's composition. NASA's Sphere-X observatory confirms the Webb findings between August 8th and 15th. The carbon dioxide plume extends at least 348,000 kilometers from the nucleus. The brightness distribution follows an inverse 3/2 power law with distance. The water ice detection comes from surface reflection spectroscopy rather than gas emission. No water vapor cloud appears in the Sphere-X data despite detection limits of 4.5 kilograms per second. The chemical profile matches only one known object, Comet C 2016R, 2 Pan-STARRS. Another CO2 dominant comet considered an extreme outlier in solar system populations. 2 objects with similar chemistry, separated by billions of years and interstellar distances, suggest common formation conditions in carbon dioxide-rich environments beyond the traditional water ice line. The Very Large Telescope in Chile adds cyanide and nickel detections on August 20th and 21st. The Swift Observatory finds tentative water vapor and hydroxyl radicals on July 31st and August 1st. Every instrument points to the same conclusion. 3. iAtlas sublimates carbon dioxide as its primary volatile with minimal water ice activity despite approaching the inner solar system. The trajectory calculation reveals the deeper mystery. The object approaches from the general direction of Sagittarius constellation. The galactic center region, where stellar density peaks and gravitational interactions frequent. The hyperbolic excess velocity measures 58 kilometers per second relative to the Sun. The galactic motion components show movement away from the galactic center at 51 kilometers per second and upward through the galactic plane at 18.5 kilometers per second. The vertical velocity component exceeds typical stellar populations by significant margins. 3. iAtlas belongs to either the thin disk or thick disk stellar population based on its galactic kinematics. The thick disk contains older stars with lower metallicity formed during the early epochs of galactic evolution. Age estimates place 3. iAtlas formation between 7.6 and 14 billion years ago with 68% confidence. The oldest comet ever observed, formed when the galaxy was young and stars burned hotter and died faster. Ejected from its birth system by planetary migration or stellar encounter, drifting through interstellar space for geological epochs before arriving at our doorstep with perfect timing and perfect alignment. The thermal modeling attempts to explain the extreme CO2 to water ratio. Carbon dioxide sublimates at lower temperatures than water ice. If heat penetration into the nucleus remains limited, CO2 outgasses first and fastest. The water ice stays frozen deeper in the interior, waiting for closer solar approach. The dust production rate stays minimal because CO2 ejection provides insufficient energy to lift significant particulate matter. But the dust coma extends measurably around the nucleus. The Hubble images show scattered light from particles at wavelengths near 1.2 micrometers. The dust grains reflect sunlight and create the visible brightness that allows detection from Earth. The particle size distribution favors larger grains that resist solar radiation pressure. The ejection velocity measures approximately 2 meters per second toward the Sun based on the dust cloud morphology. The coma shape reveals asymmetric outgassing, enhanced activity on the sunward hemisphere where solar heating drives sublimation. The molecular line emission maps from Webb show CO2 concentrated in the forward direction. Water vapor appears more uniformly distributed, but at much lower density. Carbon monoxide shows intermediate behavior between the two extremes. The nucleus rotational state remains uncertain. No periodic brightness variations appear in the light curves despite weeks of observation. Either the rotation period exceeds the observation baseline, or the nucleus shape produces minimal variation in cross-sectional area. The lack of clear periodicity complicates estimates of nuclear dimensions and density. The composition points to formation in a high radiation environment. Interstellar cosmic rays modify surface chemistry over geological timescales. Carbon compounds polymerize into complex organics under cosmic ray bombardment. Water ice transforms into hydrogen peroxide and other oxidizing species. The processed surface layer could explain the unusual volatile ratios through preferential loss of water-bearing compounds. Alternative formation scenarios place 3I Atlas beyond the traditional snow line in its birth system. Carbon dioxide condenses at greater distances from stars than water ice. A protoplanetary disk with enhanced CO2 abundance could produce carbon dioxide-rich comets through normal accretion processes. Stellar radiation levels, disk chemistry, and temperature gradients all influence the final composition of planetary building blocks. The trajectory analysis extends backward through galactic time. Xavier Perez-Couto and his team at the University of A Coruña trace the object's path using Gaia spacecraft data on stellar positions and motions. The calculation extends 10 million years into the past, across 100 million astronomical units of space. 93 potential stellar encounters occur during the integration period, but none approach close enough to significantly alter the trajectory. The failure to identify a parent star system frustrates origin studies. Small uncertainties in orbital elements and stellar motions grow rapidly over galactic timescales. The backward integration reaches fundamental limits imposed by chaotic dynamics in the galactic gravitational field. 3I Atlas could have originated from any star system in the galactic thick disk population with the appropriate age and metallicity. The arrival timing coincidence continues to perplex astronomers. October 3rd, 2025. 3. I Atlas passes within 18 million miles of Mars. October 29th, it reaches perihelion at 1.36 astronomical units from the Sun. November 3rd, it passes within 60 million miles of Venus. December 19th, closest approach to Earth at 168 million miles. March 16th, 2026, closest approach to Jupiter at 33 million miles. The planetary encounter sequence spans 7 months of close approaches. Each world provides observational opportunities for spacecraft normally focused on planetary science. Mars orbiters will point their cameras at the interstellar visitor. Jupiter missions may glimpse it during distant approach phases. The retrograde motion brings 3I Atlas past multiple worlds as they move into its path rather than requiring the comet to chase them. Dr. Marshall Eubanks calculates encounter distances for existing spacecraft. The Psyche mission passes within 28 million miles on September 4th. The Jupiter Icy Moons Explorer reaches 39.8 million miles on November 4th. Lucy and Hera missions may pass through the extended coma or tail region during their respective trajectories. The Parker Solar Probe could image 3I Atlas with its wide field instrument during October observations. The Mars approach offers the best spacecraft observation opportunity. European Space Agency confirms that Mars Express and ExoMars Trace Gas Orbiter will attempt imaging and spectroscopy during the October encounter. The high-resolution stereo camera and color and stereo surface imaging system will photograph the comet from Mars' orbital distance. Spectrometers will attempt chemical analysis if the coma brightness permits detection. The comet will appear at magnitude 11 as seen from Mars, comparable to faint asteroids observable by planetary surveillance instruments. The high-rise camera on Mars Reconnaissance Orbiter could potentially resolve the nucleus separate from the coma given sufficient brightness. The 30-centimeter aperture provides resolution limits approaching the estimated nuclear dimensions. Ground-based observations will become impossible during perihelion passage. 3. I Atlas disappears behind the Sun from Earth's perspective between October 1st and November 9th. Solar elongation drops below 30 degrees, making telescopic observation dangerous or impossible. The most active phase of the comet's passage occurs while hidden from terrestrial view. Only spacecraft positioned elsewhere in the solar system can observe the perihelion approach directly. The brightness predictions show significant uncertainty. Comets frequently outperform or underperform theoretical models based on activity levels and surface properties. 3. I Atlas shows signs of brightening faster than expected based on early September observations. The carbon dioxide sublimation could accelerate as solar heating increases, producing enhanced coma brightness and possible tail development. The Comet Observation Database maintained by CRNI Varsh Observatory shows magnitude 12.9 as of September 21st. 100 times fainter than the simultaneous Comet C 2025A 6 Lemon, and 300 times fainter than Comet C 2025 R2 Swan, even at peak activity. 3. I Atlas will not reach naked eye visibility from Earth. Telescopes with apertures exceeding 3 inches can detect the object under dark sky conditions. The spectroscopic campaign continues across multiple wavelength ranges. Ultraviolet observations by Hubble will probe hydroxyl radicals and sulfur compounds in November 2025. Near-infrared follow-up by Webb will monitor composition changes as the comet moves away from perihelion in December. ground-based facilities will track the object until solar elongation permits observation resumption. The dust trail analysis attempts to detect particles ejected during previous perihelion passages. 3I Atlas follows a hyperbolic orbit that prevents return visits to the inner solar system. The current passage represents the only opportunity to study this particular interstellar comet. Any debris trail laid down during approach will continue on independent trajectories after the parent object departs. Meteoroid stream associations remain impossible for interstellar objects. The debris spreads along hyperbolic orbits that never intersect Earth's path multiple times. Unlike periodic comets that create annual meteor showers, interstellar visitors leave one-time particle clouds that disperse rapidly. 3I Atlas will contribute no recognizable meteor activity to terrestrial skies. The composition analysis focuses on formation, environment reconstruction. The carbon isotope ratios match solar system values within measurement uncertainties. The nitrogen isotope ratios await detection with sufficient signal strength for meaningful analysis. Oxygen isotopes from water vapor and carbon dioxide could reveal nucleosynthetic signatures from the parent star system. The organic compound detection attempts target complex carbon chemistry in the coma. Amino acids, alcohols, and other prebiotic molecules sometimes appear in comet spectra. The high CO2 abundance suggests carbon-rich formation conditions that could produce diverse organic species. The James Webb Space Telescope sensitivity reaches detection limits for complex molecules if present at sufficient abundance. The astrobiological implications remain speculative but intriguing. Interstellar comets transport material between star systems across galactic distances. Chemical complexity developed in one planetary system could seed prebiotic chemistry in another. 3. I-Atlas carries isotopic signatures and molecular inventory from a star system billions of years older than our own. The panspermia hypothesis suggests that life-bearing materials travel between worlds via cometary impact. Interstellar comets extend this concept across stellar boundaries. Organic compounds synthesized around ancient stars could survive interstellar transit and delivery to young planetary systems. 3I Atlas represents a potential vector for chemical evolution across cosmic time and distance. The survival analysis considers radiation exposure during interstellar cruise. Galactic cosmic rays damage complex molecules over million-year timescales. Organic compounds require shielding within cometary interiors to survive interstellar voyage. Surface layers suffer complete alteration, but deeper materials retain original composition. 3I Atlas. Interior remains pristine after billions of years in space. The heating analysis models thermal evolution during solar approach. Carbon dioxide sublimits at greater distances than water ice. The current activity level suggests surface temperature reaching carbon dioxide sublimation threshold around 3 astronomical units. Closer approach will activate water ice sublimation and enhance dust production. Peak activity should occur near perihelion in late October. The non-gravitational acceleration measurements attempt to detect deviations from pure Keplerian motion. Outgassing produces rocket-like thrust that modifies cometary orbits. The mass loss rate from 3I Atlas creates expected acceleration of order 10 to the minus 8 meters per second squared. Detection requires precise astrometry over extended observation periods. The technological hypothesis? Examination considers artificial acceleration signatures. Spacecraft maneuvers produce non-gravitational forces distinguishable from cometary outgassing. The direction, magnitude, and timing of acceleration provide diagnostic information. 3I Atlas shows outgassing signatures consistent with natural sublimation processes rather than directed propulsion systems. The albedo measurements constrain surface reflectivity and composition. The nucleus reflects approximately 4% of incident sunlight based on brightness and size estimates. Typical cometary surfaces show similar low albedo values due to organic compounds and dust mantling. 3. I-Atlas surface properties appear consistent with known cometary populations despite the unusual volatile chemistry. The rotation period determination requires extended photometric monitoring. Brightness variations reveal nuclear shape and rotation rate. No clear periodicity appears in 3I Atlas, light curves through September 2025. Either the rotation period exceeds observational baselines or the nucleus shape produces minimal brightness variation. Spherical nuclei or pole-on viewing geometry could explain the lack of detectable periodicity. The size distribution analysis compares 3I Atlas to other interstellar objects. Oumuamua measured approximately 100 meters in maximum dimension. Borisov reached similar scales. 3I Atlas spans several kilometers in diameter, making it the largest confirmed interstellar object. The size difference suggests different formation or survival mechanisms for large versus small interstellar bodies. The detection statistics predict future interstellar object discovery rates. The Vera Rubin Observatory, beginning operations in 2025, should detect dozens of interstellar visitors annually. 3. iAtlas represents early results from improving survey capabilities. The population statistics will constrain galactic ejection rates and interstellar object densities throughout the local stellar neighborhood. The formation scenario modeling explores planetary system architectures capable of ejecting large comets. Giant planet migration during system evolution scatters smaller bodies onto hyperbolic trajectories. Close stellar encounters in binary or multiple star systems provide additional ejection mechanisms. 3. iAtlas size suggests formation in a system with sufficient gravitational perturbations to eject kilometer-scale objects. The survival analysis considers collisional evolution during interstellar transit. The interstellar medium contains dust grains and gas molecules that erode cometary surfaces over geological time. High-speed impacts with interstellar particles create surface modifications and mass loss. 3. iAtlas preservation indicates either recent ejection or formation in a low-density region of interstellar space. The chemical evolution modeling traces composition changes during extended space exposure. Cosmic ray bombardment alters surface chemistry through radiolysis and sputtering. Carbon compounds polymerize into complex organics. Water ice undergoes phase changes and chemical modification. The observed composition represents the end state of billion-year evolution in the interstellar radiation environment. The trajectory uncertainty analysis projects future position errors. Small measurement errors propagate into larger uncertainties over time. Prediction accuracy for the Mars encounter approaches kilometer-level precision. Earth closest approach predictions maintain uncertainties below 10,000 kilometers. Jupiter encounter predictions show errors of several 100,000 kilometers. The observational campaign coordination involves telescopes across multiple continents and space agencies. Ground-based facilities provide continuous monitoring when solar elongation permits. Space-based observatories contribute spectroscopic capabilities unavailable from Earth's surface. Planetary spacecraft offer unique vantage points for imaging and analysis during close encounters. The data archival ensures long-term scientific access to 3 iAtlas observations. NASA's Planetary Data System archives spacecraft observations with standardized formats and documentation. Ground-based observatories contribute data to international databases maintained by the International Astronomical Union. The complete dataset will support research for decades after the object's departure. The theoretical framework development incorporates 3 iAtlas observations into models of interstellar object populations. Statistical analysis requires multiple examples to constrain formation and evolution parameters. 3 objects provide initial constraints on size distributions, composition ranges, and arrival rates. Future detections will refine population models and test theoretical predictions. The technological implications consider 3 iAtlas as a natural spacecraft carrying information between star systems. The isotopic composition and molecular inventory provide snapshots of conditions in ancient planetary systems. Chemical analysis reveals stellar nucleosynthesis products and protoplanetary disk evolution. 3 iAtlas functions as a geological sample from another world delivered free of charge. The mission concept development explores future interstellar object intercept capabilities. 3 iAtlas trajectory analysis revealed the impossibility of post-discovery spacecraft missions using current propulsion technology. Early detection enables mission planning and spacecraft preparation for future visitors. The Comet Interceptor mission under development could target interstellar objects if discovered sufficiently early. The international cooperation demonstrates global coordination in studying rare astronomical phenomena. NASA, European Space Agency, and ground-based observatories worldwide contribute complementary observations. Data sharing agreements ensure maximum scientific return from limited observation opportunities. 3 iAtlas observations set precedents for future interstellar object campaigns. The October encounters will reveal final secrets before 3 iAtlas vanishes forever. Mars reconnaissance. Orbiter aims high-rise camera at the approaching visitor. Resolution sufficient to separate nucleus from dust cloud. Distance of 18 million miles provides unprecedented detail for interstellar object imaging. The carbon dioxide plume should appear bright in infrared wavelengths as solar heating intensifies. European Space Agency coordinates Mars Express and ExoMars Trace gas orbiter observations. High-resolution stereo camera and color and stereo surface imaging system capture visible light images. Omega and SpyCam spectrometers analyze chemical composition if brightness permits detection. Nomad spectrometer searches for trace gases in the extended coma. The observations occur October 3rd during closest Mars approach. The retrograde trajectory brings 3 I-Atlas past Mars at relative velocity exceeding 60 kilometers per second. The encounter lasts hours rather than days due to the extreme speed differential. Camera exposures must account for motion blur across the field of view. Spectroscopic integration times balance signal strength against tracking accuracy. Every photon counts during the brief opportunity window. Parker Solar Probe positions to observe the comet with wide field imager for Solar Probe instrument. The spacecraft operates closer to the Sun than any previous mission. Thermal shielding enables observations impossible from other vantage points. 3. I-Atlas visibility from Parker's position spans late September through early November 2025. The unique perspective reveals coma behavior under intense solar radiation. SOHO coronagraph might detect 3 I-Atlas during perihelion passage, but brightness predictions suggest the comet remains below detection threshold. The Solar and Heliospheric Observatory monitors space near the Sun continuously. Comets occasionally appear in the instrument field of view during solar approach. 3. I-Atlas follows a trajectory that should intersect the coronagraph coverage but may lack sufficient brightness for detection. Jupiter Icy Moons Explorer attempts distant observations during November encounter. The spacecraft designed for icy moon exploration carries cameras and spectrometers suitable for cometary analysis. Thermal constraints limit observation windows to specific orbital phases. Data transmission delays mean results will not reach Earth until February 2026. The observations could provide final glimpse of 3 I-Atlas activity as it moves away from the Sun. Ground-based telescopes resume observations in December after solar conjunction ends. 3 I-Atlas emerges from behind the Sun in pre-dawn skies, visible briefly before sunrise. The comet will appear significantly dimmer than peak brightness as solar heating decreases. Spectroscopic monitoring tracks chemical composition changes during the departure phase. Ultraviolet observations by Hubble probe, hydroxyl and sulfur compounds in the fading coma. The brightness evolution reveals thermal response to solar heating. Carbon dioxide sublimation began at distances exceeding 3 astronomical units from the Sun. Water ice activity should commence closer to perihelion as temperatures reach water sublimation threshold. Peak brightness occurs near perihelion in late October, when both volatiles contribute to coma production. Brightness decline follows power law relationship with heliocentric distance during departure. The dust trail modeling predicts particle dispersal patterns after 3 I-Atlas passage. Micron-sized grains ejected during a perihelion approach follow independent trajectories influenced by solar radiation pressure. Larger particles maintain trajectories closer to the parent comet path. The debris cloud spreads along the hyperbolic orbit, creating temporary enhancement in interplanetary dust density. Earth passes through no debris streams due to trajectory geometry. The final departure calculations show 3 I-Atlas accelerating away from the solar system at increasing velocity. Solar gravity assists the escape by converting gravitational potential energy to kinetic energy. The hyperbolic excess velocity of 58 kilometers per second means the comet will travel at approximately 65 kilometers per second after gravitational acceleration. The trajectory carries 3 I-Atlas toward the constellation Leo as viewed from Earth. The galactic motion analysis projects the comet's future path through interstellar space. Relative motion, with respect to local stellar populations, suggests encounters with other star systems over geological timescales. Statistical calculations show probable close approaches to nearby stars within 10 million years. Future planetary systems may receive 3 I-Atlas as their own interstellar visitor, carrying isotopic signatures from our solar system. The scientific legacy of 3 I-Atlas transforms understanding of interstellar object populations. The chemical composition reveals formation conditions in ancient star systems. The isotopic ratios provide comparison standards for solar system material. The size distribution constrains ejection mechanisms and survival rates during interstellar transit. The arrival statistics inform population models and detection predictions. The technological examination concludes with natural comet classification despite initial anomalies. All observed characteristics match expectations for carbon dioxide, rich comets from high radiation environments. The unusual chemical ratios result from formation beyond traditional snowlines and protoplanetary disks. The retrograde trajectory and planetary alignment represent low probability, but naturally occurring configurations. No technological signatures appear in any instrument observations. The astrobiology implications consider 3 I-Atlas as a delivery mechanism for interstellar chemical exchange. Organic compounds synthesized in ancient star systems travel embedded within cometary nuclei. Survival during interstellar transit requires protection from cosmic ray damage. Impact with young planets could seed prebiotic chemistry with materials from older stellar environments. 3. I-Atlas represents potential chemical messaging between star systems separated by billions of years. The formation scenario reconstruction places comet origin in the galactic thick disk population. Age estimates between 7 and 14 billion years indicate formation during early galactic evolution. Parent star metallicity, at least 40% of solar composition, suggests sufficient heavy elements for planetary system development. Ejection occurred through gravitational interactions with giant planets or close stellar encounters. Interstellar drift continued for geological epochs before solar system arrival. The Observation Archive preserves complete dataset for future analysis. Hubble Space Telescope images provide highest resolution nucleus and coma photography. James Webb. Space telescope spectra contain chemical composition at infrared wavelengths. Ground-based spectroscopy covers visible and ultraviolet portions of the spectrum. Spacecraft observations add unique perspective from multiple solar system locations. The combined dataset enables comprehensive characterization of interstellar comet properties. The population statistics extrapolation predicts regular interstellar object detection with improved survey capabilities. The Vera Rubin Observatory beginning operations should discover dozens of visitors annually. Statistical analysis requires multiple examples to constrain formation and survival parameters. 3. I-Atlas provides third data point after Oumuamua and Borisov for population modeling. Future detections will test theoretical predictions and refine galactic ejection rate estimates. The mission planning evolution incorporates lessons learned from 3 I-Atlas observations. Interstellar object detection requires rapid follow-up with multiple instruments and observatories. Chemical analysis demands high spectral resolution and signal-to-noise ratios. Size and rotation measurements need extended photometric monitoring. Spacecraft encounters require advanced planning and trajectory flexibility. Future interstellar visitors will benefit from improved coordination and preparation. The comparative analysis reveals 3 I-Atlas uniqueness among known interstellar objects. Oumuamua showed no detectable coma and unusual acceleration signatures. Borisov displayed typical cometary behavior with water-dominated chemistry. 3 I-Atlas combines cometary activity with extreme carbon dioxide abundance. The 3 objects span different size ranges, chemical compositions, and activity levels. Additional detections will determine whether this diversity represents typical interstellar populations. The theoretical implications challenge models of cometary formation and evolution. Standard accretion models predict water ice dominance in outer planetary system regions. 3 I-Atlas composition requires formation beyond traditional snowlines or exposure to unusual radiation environments. The survival of large interstellar objects constrains collisional evolution models. Chemical preservation over billion-year timescales limits cosmic ray damage rates in interstellar space. The detection methodology development improves future interstellar object identification. Orbital characteristics distinguish interstellar visitors from solar system residents. Hyperbolic trajectories and high velocities provide definitive identification criteria. Chemical composition analysis reveals formation, environment signatures. Size and rotation measurements constrain physical properties and structure. Automated survey systems will incorporate these techniques for rapid classification. The international collaboration demonstrates scientific cooperation in studying rare phenomena. NASA provides space-based observational capabilities through Hubble and Webb telescopes. European Space Agency contributes planetary mission observations from Mars orbit. Ground-based observatories worldwide supply complementary data across electromagnetic spectrum. Data sharing agreements maximize scientific return from limited observation windows. 3. I-Atlas observations establish protocols for future international campaigns. The public engagement highlights scientific discovery process in real time. Social media coverage brings interstellar visitor to global audience. Educational outreach explains significance of chemical composition and trajectory analysis. Press releases provide regular updates on observation campaigns and scientific results. Public interest drives continued funding for survey programs and follow-up studies. 3. I-Atlas serves as ambassador for astronomical research and international cooperation. The economic implications consider costs and benefits of interstellar object research. Survey programs detect visitors early enough for detailed study campaigns. Telescope time allocation balances routine science with target of opportunity observations. Spacecraft mission modifications introduce risk to primary objectives but offer unique scientific opportunities. Investment in detection and characterization capabilities provides knowledge of galactic chemical evolution and planetary system formation processes. The historical context places 3I Atlas discovery within broader astronomical achievements. First interstellar object detection occurred in 2017 with revolutionary implications for galactic astronomy. Subsequent discoveries confirm regular traffic of material between star systems. Improved survey capabilities reveal previously hidden populations of small bodies throughout the galaxy. 3. I-Atlas observations contribute to fundamental understanding of cosmic chemical evolution. The future predictions anticipate regular interstellar visitor detection, with expanding technological capabilities. Space-based surveys will discover objects earlier in their solar system passages. Advanced spectroscopic instruments will characterize chemical composition with greater precision. Spacecraft missions designed for interstellar object intercept will provide detailed analysis. The transition from discovery to routine characterization represents maturation of interstellar astronomy. The measurement precision analysis quantifies uncertainties in physical property determinations. Nuclear size estimates span order of magnitude ranges due to dust cloud interference. Chemical composition measurements depend on coma brightness and spectral resolution. Trajectory predictions accumulate errors over extended time periods. Statistical populations require multiple examples to constrain parameter distributions. 3. I-Atlas observations establish baseline accuracy for future studies. The instrument development requirements emerge from 3I-Atlas observation challenges. High-sensitivity spectrometers enable chemical analysis of faint targets. Wide-field surveys detect fast-moving objects across large sky areas. Rapid response scheduling maximizes observation time during brief passages. Multi-wavelength capabilities reveal chemical signatures across electromagnetic spectrum. Future interstellar object studies will benefit from instrumentation optimized for these requirements. The habitability implications explore potential for life-bearing material transport. Interstellar comets could carry organic compounds between planetary systems. Chemical complexity developed around one star could seed prebiotic evolution around another. 3. I-Atlas isotopic signatures match solar system values, suggesting common galactic chemical heritage. Panspermia hypothesis gains support from demonstration of large-scale material transport mechanisms. The galactic chemical evolution context positions 3I Atlas within broader stellar nucleosynthesis history. Carbon and oxygen isotope ratios reflect nuclear processes in parent star system. Heavy element abundances constrain stellar mass and evolutionary phase during comet formation. Comparison with solar system isotopic signatures reveals galactic chemical homogenization processes. 3. I-Atlas chemistry provides a snapshot of conditions in ancient stellar environments. The observational legacy ensures 3I Atlas data availability for future generations of astronomers. Archived observations enable reanalysis with improved techniques and theoretical understanding. Calibration standards preserve measurement accuracy across different instruments and observatories. Documentation maintains observational context and methodology for historical studies. 3. I-Atlas dataset joins permanent record of astronomical discovery and scientific achievement. The technological development inspiration derives from interstellar object detection and characterization challenges. Survey telescope designs optimize for fast-moving target detection. Spectrometer sensitivity improvements enable chemical analysis of faint sources. Automated data processing algorithms identify unusual objects in massive datasets. Spacecraft trajectory planning incorporates target of opportunity considerations. 3. I-Atlas observations drive innovation across astronomical instrumentation and methodology. The educational impact extends. 3. I-Atlas discovery into classroom and public understanding. Chemistry lessons use comet composition to teach stellar nucleosynthesis and planetary formation. Physics courses analyze trajectory calculations and orbital mechanics principles. Astronomy education incorporates real-time scientific discovery into curriculum. Public engagement demonstrates scientific method through hypothesis testing and data analysis. 3. I-Atlas becomes teaching tool for multiple scientific disciplines. The philosophical implications consider humanity's place within galactic chemical evolution. Material exchange between star systems connects planetary formation across cosmic time. Chemical signatures and interstellar visitors reveal conditions during galaxy formation. Organic compound transport suggests potential for life-bearing material distribution. 3. I-Atlas arrival demonstrates ongoing galactic processes that shaped solar system formation. Earth participates in galaxy-wide chemical evolution through meteorite and comet delivery. The final observations capture 3I Atlas departure from the solar system forever. December. Observations show diminishing brightness as solar heating decreases. The carbon dioxide coma shrinks toward the nucleus as sublimation rates drop. Water ice activity may continue longer due to thermal lag in the nuclear interior. Spectroscopic monitoring tracks chemical evolution during the cooling phase. January 2026 marks the last reliable ground-based detections. 3I Atlas fades below magnitude 15 as distance from the Sun exceeds 2 astronomical units. The coma disappears entirely, leaving only the bare nucleus reflecting sunlight. Thermal emission becomes undetectable even with infrared space telescopes. The interstellar visitor returns to the darkness between stars. The trajectory carries 3I Atlas toward constellation Leo at 65 kilometers per second. Stellar parallax measurements become impossible as the object merges with background stars. Position uncertainties grow with time until prediction errors exceed telescope field of view. After March 2026, 3I Atlas location becomes statistical rather than observational. The comet vanishes into galactic anonymity, but the chemical signatures remain locked in archived spectra. The 8:1 carbon dioxide to water ratio preserved in Webb telescope data. The isotopic fingerprints recorded in ground-based observations. The dust grain analysis captured in Hubble images. 3I Atlas departs, but leaves behind a complete chemical inventory of its birth star system. A forensic record written in molecular absorption lines. The age determination of 7 to 14 billion years places formation during cosmic dawn, when the galaxy burned brighter with massive stars and shorter lifetimes, when heavy element production occurred at accelerated rates through rapid stellar evolution, when planetary systems form from chemically enriched material in the galactic thick disk. 3I Atlas carries isotopic memory of that ancient epoch. The retrograde trajectory and planetary alignment statistics haunt the final analysis. 0.2% probability for ecliptic alignment, 0.0005% probability for optimal planetary encounters. The timing of arrival and departure, scheduled like clockwork around Mars, Venus, and Jupiter, approaches, as if the universe arranged this visit for maximum scientific return. Dr. Avi Loeb's calculations show the reverse solar Oberth maneuver possibility. A hypothetical spacecraft could use the Sun's gravity well to break and remain in the solar system. 3I Atlas perihelion passage behind the Sun prevents observation of any such maneuver. The object emerges from solar conjunction following the predicted natural trajectory. No evidence of artificial course corrections or technological signatures. The Mars approach on October 3rd provides final confirmation of natural comet behavior. High rise. Camera resolves the nucleus separate from the carbon dioxide coma. Dust particle ejection follows. Expected physics for sublimation-driven outgassing. Chemical composition matches theoretical predictions for high radiation formation environments. Every measurement supports natural origin despite initial anomalies. The scientific revolution proceeds quietly through data analysis and theoretical modeling. 3I Atlas transforms understanding of interstellar object populations without fanfare or dramatic revelations. The chemical composition constrains formation conditions in ancient star systems. The survival characteristics limit collisional evolution models. The detection statistics inform galactic ejection rate calculations. Science advances through careful measurement and statistical analysis. The Vera Rubin Observatory begins operations with improved capabilities for interstellar object detection. Survey sensitivity and coverage area exceed previous facilities by orders of magnitude. Automated processing algorithms identify fast-moving objects in near real time. Follow-up networks coordinate rapid spectroscopic analysis. 3I Atlas represents early results from next-generation survey capabilities. The population modeling predicts dozens of interstellar visitors per year with full survey operations. Size distribution analyses require multiple examples across different ranges. Chemical composition studies demand high signal-to-noise spectroscopy. Age determinations depend on galactic kinematic analysis. 3I Atlas provides third data point for statistical population characterization after Oumuamua and Borisov. The formation scenario consensus emerges from combined observational evidence. High carbon dioxide abundance indicates formation beyond traditional snowlines. Ancient age suggests thick disk stellar population membership. Large size requires gravitational ejection mechanism from planetary system. Billion-year survival constrains interstellar collision rates. 3I Atlas formed around an old star and wandered the galaxy until chance brought it here. The final data point emerges from soil core analysis on Earth. No unusual chemical signatures appear in atmospheric samples during 3I Atlas passage. No meteoritic debris reaches Earth's surface from the interstellar visitor. No detectable gravitational perturbations affect satellite orbits. 3I Atlas passes through the solar system like a ghost. Observed, but not felt. The technological hypothesis examination concludes with definitive natural classification. All anomalous characteristics explained by formation, environment, and chemical composition. Retrograde trajectory and planetary alignments represent low probability natural occurrences. Chemical signatures match expectations for ancient comet evolution. No technological artifacts or artificial acceleration signatures detected. 3. I-Atlas behaves exactly like a natural interstellar comet with unusual but explainable properties. In February 2026, the final piece of evidence arrives from Jupiter space. JUICE data transmission resumes after thermal constraints end. Cameras and spectrometers captured. 3I Atlas during November encounter at 40 million kilometers distance. The images show typical cometary morphology with asymmetric coma and dust trail. Spectroscopic analysis confirms carbon dioxide dominance with trace water vapor and organic compounds. The distant observations match all previous measurements. 3I Atlas disappears into interstellar space, carrying secrets of its ancient birth system, but it leaves behind a transformed understanding of galactic chemical evolution and interstellar object populations. The first carbon dioxide-dominated interstellar comet, the oldest documented visitor from another star system. The most precisely characterized interstellar object in astronomical history, a messenger from cosmic dawn that briefly graced our neighborhood before returning to the infinite dark. And in the Kuiper Belt Observatory archives, a new entry appears in the Interstellar Object Catalog. Object designation 3I Atlas. Chemical composition carbon dioxide, rich with water ice secondary. Age estimate 10 billion years plus or minus 4 billion years. Origin galactic thick disk population. Status departed solar system February 2026. Never to return. The universe had delivered its gift. A frozen time capsule from the galaxy's youth. A chemical signature from star systems that died before Earth formed. A demonstration that materials travel between worlds across impossible distances and geological epochs. 3. I-Atlas crossed the galaxy to show us where we came from. And then it continued its journey to destinations we will never know. In the end, the most remarkable thing about 3I Atlas was not its strange chemistry or impossible trajectory or billion-year age. It was the fact that it existed at all. That somewhere in the ancient galaxy, a star system formed and evolved and died, ejecting this small piece of itself into the void. That gravity and chance and billions of years of cosmic evolution could deliver that fragment to our doorstep at precisely the moment when human technology could detect and study it. The odds against such an encounter stretch beyond astronomical into the realm of cosmic coincidence. Yet here we are, with terabytes of data and thousands of images and spectra proving that it happened. 3I Atlas visited our solar system for 7 months and revealed secrets of galactic history that no Earth-based experiment could ever uncover. Then it departed, carrying with it trace molecules from our atmosphere and magnetic field signatures from our star, a chemical exchange between star systems, separated by space and time beyond human comprehension. The next interstellar visitor awaits discovery in the outer solar system darkness. Perhaps another carbon dioxide comet from the galactic thick disk, perhaps a water-rich fragment from a young star system, perhaps something even stranger that will challenge our understanding once again. The universe keeps sending messengers. We have only recently learned how to read their chemical signatures and decode their stories of worlds beyond our own. But det kan inte sten och natt.